So I will take the first half of this presentation here, and Peter will join us for the second half. So bear with us for the small changing scene here. Sorry, Phil, did you have a question before I move in?
Please begin when you're ready.
Thank you very much. Okay, anyway, thank you all for giving us the opportunity to show our work here. We are both very sorry we couldn't join you in London, but hope to be able to do that for MSS too, of course. Anyway, I'm going to take a part of the Star Tracker in-flight checkout part. Peter Brauer will join us for the vector field magnetometer. I got a lot of stuff I want to show you, so I'll just throttle on here. So just to put it a little into perspective, we have 3 Star Trackers on board. They look like this. They are approximately 5 centimeters from corner to corner. So it's a nice little handful. The 3 camera heads are mounted in an orthogonal geometry, as seen here, with all the light shades on. Not to get too much disturbed by the sun and earth light. We denote them camera head unit 1, A, B, and C, as shown in the picture here. And they are sitting on a magneto-optical bench together with a vector field magnetometer at the end here. So first of all, I've been looking at data covering the range from August 6th through August 28th, roughly 25 days of data. Most of them are complete 24-hour data, some only 16-hour data. They are almost complete. I do see a little 1-second gap during some very remarkable times around midnight and 1600 hours. I strongly suspect that this is some kind of ground-based processing that introduces this delay here, these small outages. So basically, almost to 100% of data completeness, which is good. What I also look at is how well is the optical axis has been changed by launch loads, and I do that by requesting 10 to 15 Star Tracker images being dumped. We basically have 4 parameters that we describe the optical system from. We have 2 giving the intersection with the CCD, optical axis intersection with the CCD. And we have 2 parameters covering the effects of focal length and the radial distortion. So I usually make this projection, plane projection, one giving the CCD and one giving the effects of focal length and distortion parameters. There's one for each of the camera head units, and essentially each one of these images that we acquire, I run a parameter kind of optimization test to get the least stress between the star catalog and the image we observe, and it gives one set of parameters. And if I plot them in these projections, we can easily see that they circle around the same area. We have blue here. This is the post-production values. We got the red ones. Those are the ones that was captured after environmental testing on the ground. And then finally, we have the yellow points, and these are from the images that are acquired in flight. So all in all, we have good agreement with the parameters captured during all 3 events or times, which means we have an optical system that is not being impacted by launch loads. I also look at system gain, and this is more specifically how much light should we expect in digital numbers after quantization as function of how much light is coming in. That's extremely difficult to calibrate accurately on ground. We have the stars. They are a very, very well established intensity, but we are monitoring them through an extincting atmosphere, of course. So just to show you what we're up against here, the blue curve again is post-production. So these are from the 10 images that we captured following production, and they are captured in the Copenhagen area, which means that it's roughly sea level through a lot of atmosphere. The second post environmental test, we move to a mountaintop, 2 kilometers of altitude, and take another set of images, and we get a somewhat better gain. This time we are roughly 5.8. And again, from in-flight, we measure even a higher gain. So we can use these as estimators for how much gain do we see in flight, but the actual levels we need to characterize in flight. Anyway, these are very close to the expectations, and I still have a little work to look into some of the in-flight data to see if we can tweak this a little to get a little more juice out of the star trackers, but we are looking at almost optimal levels with this curve here. Third thing, trying to characterize the accuracy of the star trackers. This is always difficult because we don't really have any ground truth. But since we have 3 different star trackers, what I can do is that I can use one star tracker as a reference for another star tracker, which essentially gives me 3 different possible pairs of star trackers. Camera AB, AC, and BC. And by measuring the angle between the bore sides, I can plot this over time. This is from 16 hours of data. You can see there are some small gaps. That's when one of the camera heads are close to the inside the exclusion cone of the sun. It simply gets blinded by the sun, so I have no data at this time here. But anyway, looking at the variation of this inter-boreside angle over time, I can get a conservative estimate for what the accuracy of the star tracker head is. I say conservative here, upper estimate, because this is everything included. This is also deformation of optical bends from heating of the star trackers. This is caused by includes daylight effects when we are just close to the exclusion cones. And it also contains residual from aberration correction. You can see one of the examples. There's a very fixed pattern when we are moving out from this solar blinding here. There's a little too fast here. There's a little excursion until we are back into the bias level here. Anyway, looking at these daily RMS figures, I get something like this. During this period, we had the aberration correction turned off, so we have expectedly higher levels during this time here. But in this year, we are running close to optimal, and we see that we have accuracy figures in the range of 2.5 arc seconds per second. So how does this compare with swarm? I took swarm data from the exact same day. I tried to align the data sets. Swarm is operating 2 Hertz, so I decimated to 1 Hertz using averaging. Also, I used the Macau data, MSS1 data, and converted them also to 1 Hertz data. I did aberration correction on the swarm data. This is not done in flight. This is done as post-processing on the ground. And I end up with 3 different pairs on the Swarm A spacecraft for the same day, and they end up here, and from MSS1 they end up here. Now it looks like I've been doing some copy pasting here. This is not the case. They are actually almost spot on to each other's 3 different pairs here. The next decimal, there's a variation. On all circumstances, when I perform mean averaging of the heads, I end up at something that is almost unbelievably identical to what we observe on Swarm. So they compare extremely well, the star trackers on Swarm A and MSS1. So that leads me to a summary for the in-flight checkout. Data integrity looks okay. Again, strongly assume that these 1 second gaps are some kind of ground processing artifacts. All optical parameters are within expectations. I have a little work to do on the gain compensation, but from what I see here, the settings are definitely in the right ballpark. Accuracy estimation, we compare well to Swarm. So all in all, I'll say the 3 star trackers on MSS are healthy and they behave well. That's all I have. Thanks.
Thank you. Can we move to Peter?
Okay, everybody. My name is Peter Brauer, and I've been working on the Macausat VFM data. Are we sharing the screen?
We are sharing the screen.
Okay.
Seeing everything.
I'm sitting here with the project manager, Troelz. Yeah, and is that the screen that we're sharing?
Yeah.
Okay. The evaluation is based on.
Sorry, Peter, we're seeing the presenter view. Could you switch to the presentation?
Presentation. I don't know if we can do something like this.
That's it. Thanks.
Okay. So the evaluation is based on data from one day, the 22 of August. That means that it's only high frequency evaluation that we are doing, high and mid frequency evaluation. Low frequency, as in terms of drift and variations, can only be done by a scalar calibration or in-flight calibration, comparing with the scalar magnetometer. So if we look at the timing, and the magnetometer has an internal counter that is describing the time of the magnetometer, and that is used for the magnetometer sampling. By a difference analysis, we see the same missing packages that Troelz were talking about. We are seeing gaps of 1 second occasionally. For the specific day, we have lost 13 packages, and we are quite sure that these can be reconstructed after some processing of the satellite data. On Swarm, we see in the order of 1-2 packages lost per month. The drift of the internal time is due to the crystal that defines the internal time. It's an 8 megahertz clock, and that is drifting compared to the satellite time. We are doing extensive synchronization with the satellite time, so we can reconstruct the absolute time perfectly. The drift of the internal time is in the order of 64 microseconds per second, and on Swarm we have in the order of 60 microseconds. So that is very comparable to Swarm. Apart from the drift, there are some small variation in the crystal that is seen on the red curve. But they are also tracked to the absolute time of the satellite, so we can reconstruct time in the order of 10 plus minus 10 microseconds. Yeah, next. So if we look at the evaluation of the field values from the magnetometers, the 3 components, X, Y, and Z, what we do is that we look first in the derivative or the difference in the field values, seeing in the middle plot. And we are also looking at the residual plot where we take small segments of 300 seconds, fit it to a polynomial, and subtract it from the component data. The residual is then variations from a smooth variation in the field. And what you can see on the lower plot, you have some orbital variations that seems to stem from jet currents, or at least some field-aligned currents. But what is also seen is that there are some fluctuations that is not necessarily aligned with the orbit. Next slide. These variations seems to be some interference from another subsystem of the satellite. These can be studied in detail from the difference of the B field, and again subtracting the orbital variations that would reveal these interference fluctuations. On the lower right plot, you see a zoom in of such a disturbance burst. But the case is that we can identify these bursts, and if necessarily, we can flag them. As said, they are probably some interference by other instruments, but it is most likely not from a perturbation on the sensor itself, but it is an EMC interference, since it is not a specific frequency, but it's more the noise level of the instrument that is increased while we're having these interferences. If we take out data from the residual field where the disturbances are low, we can reconstruct the noise of the instrument. And what you see on the spectrum, we have a noise spectrum where at 1 Hertz we have around 11 picotesla per square root Hertz. And that is exactly the same as we have on Swarm. At the lower frequencies, we have a slightly higher increase, but that is due to variations and fluctuations in the natural variations in the field. On Swarm, we have an integral noise in the order of 25 picotesla per root mean square. On this, we can evaluate in the order of 32 picoteslas. But again, that is mostly due to the natural variation in the field. If we look at the scalar field, the constructed scalar field, we have exactly the same order of magnitude of the noise as we have on Swarm. So in summary, the data integrity of the magnetometer, the FM magnetometer, is fine. We do have some gaps, but they are likely to be reconstructed after reprocessing. The timing integrity are fine within plus minus 10 microseconds. The field component in the high frequency is fine. We do have these interference bursts, but they can be flagged. In the mid frequency, we do not see any problems at all. It's fully comparable to Swarm. And in the low frequency, it seems from the in-flight calibration that G presented that we indeed have a perfectly functioning VFM magnetometer.